Good morning. My name is Matthias Fresacher, and today I'm going to tell you about joint work I did together with James East, Azeef, Muhammed and Tim Stokes on finding a categorical representation of DRC semigroups. To begin with, a quick overview of what this talk is all about. And in fact, it's going to be two talks in one, a speed talk and the talk proper. In the speed talk, I'm just going to try and give you a big picture summary of what this project was all about. And the key aim here is just to give you an indication of the destination I'm trying to get to. The key behind giving a speed talk first is just to try and make the talk proper as accessible as possible. Because of this, I'm going to keep definitions to a minimum. In fact, I'm going to skip most of them. In the talk proper, I'm then going to repeat everything with the details and include all of the definitions we are going to need. I'm going to outline the motivation for this project that will then nicely lead into the main theorem we were able to prove, but I'm only going to give an outline of that proof as it does get a little bit technical. Instead, I'm going to focus more on the history of this particular research program and focus on putting this result in its appropriate context. To finish up with, I'm going to go through some of the applications of this work as well as some possible future directions. So let's get into it with the speed talk. And this is going to be a tale of two cities. On the one side, we have semigroup city, so that is a set together with a binary operation that is associative, and we have category city. So category, where we can think of this as a collection of objects, which I'm going to denote as just points, collection of morphisms, which map between our objects, where every object must have an identity morphism, and I have a composition operation between our morphisms, and this has to be associative. Over on semigroup city land, well there, if I take any pair of elements, the binary product is going to be defined for every pair. That means I know the full Cayley multiplication table. So for example, if I'm looking at the Brouwer monode of degree 2, if I multiply this element by this element, I would get 0. On the category city side, well here our binary product is only defined for some pairs, specifically where the domain and range appropriately match. Because of this, we only know the partial Cayley multiplication table. So in this instance, this is what it would look like. Here we can see I cannot compose f with f. F can only be composed with the identity of b, in which case I would get f. So that raises the question, why do we care about categories? Well, because they need less information. And that raises the natural question of, if I start with a partial binary operation, can I recover the full binary operation? Spoilers, yes we can, thanks to the Ehresmann-Shine-Namburi-Part ESN theorem. But this is only true for inverse semigroups. Since then, there's been a lot of effort to try and generalize this to other semigroup families. And today I'm going to talk to you about the latest installment in this research program for DRC semigroups. But this need for less information here is somewhat misleading because sadly, nothing in this world is for free. The word category does a lot of heavy lifting on that previous slide because the category needs additional structure, and that is where in essence the missing information is hiding. Generally speaking, the bigger our semigroup family, so if we say move from inverse semigroups up to DRC semigroups, the stronger our category axioms need to be, the more structure the category needs to have. So let's get into the talk proper and start off in semigroup city with the definitions we are going to need. Obviously, the main focus for this project is a DRC semigroup. So let's begin by putting a DRC semigroup into context. DRC semigroups contain the star regular semigroups. A good example of this would be the multiplicative monoids, so matrices of complex or real numbers. These contain the regular star semigroups. A good example of this would be the diagram monoids. And I do apologize for the unfortunate naming. That was not my choice. And sitting inside of the regular stars, we have the inverse semigroups. DRC semigroups also contain the Ehresmann semigroups. A good example of this would be the monoid of binary relations. Inside of Ehresmann, we find the restriction semigroups, which in turn contain the inverse semigroups. And sitting in the center here, we also have DRC restriction semigroups. What exactly is a DRC semigroup? So obviously it's going to be a semigroup, but we also have two unary operations D and R. By unary, I simply mean a map from S to S itself. These are called the domain and range operations. So to get up to a DRC semigroup, I'm just going to start off with a D semigroup. So I have a D semigroup if for every X and Y in my semigroup, these three axioms hold. And there's also a dual notion if I'm talking about an R semigroup. I can add a bit more structure in a DC semigroup, where C stands for congruence. Then I would have these three axioms holding. And again, there is a dual notion of an RC semigroup, where these three axioms would hold. If I add two more axioms that interlink the domain and range map, well, that is my DRC semigroup. So DRC semigroup, all of these axioms hold. So let's look at the inverse semigroup, but through the lens of a DRC semigroup. So inverse semigroups, they have an inverse, and I can make use of that inverse to define my domain and range operations. If I move up a little bit into the regular stars, well, I have a star operation, and I can analogously make use of that star operation to define my domain and range. If I keep going up into the star regular semigroups, I do still have the star operation, but this time I need to make use of the more Penrose inverse to define my domain and range operations. If I go over to the other side, into the Ehresmann side, well, these already come equipped with a domain and range operation, so no further work is required here. Let's go over into category city. So recall, a category is a collection of objects, which I'm just going to denote as points, a collection of morphisms, which I denote by arrows, which map between our objects, where every object has an identity morphism, and we have a way to compose our morphisms that is associative. I can add a little bit more structure in what's called a groupoid, and here every morphism needs to have an inverse. As the name suggests, this is going to generalize the notion of a group, but the key difference being that a groupoid, the binary operation is only defined for some pairs. Again, where the domain and range need to appropriately match, compared to in the group setting where the binary operation is defined for every possible pair. I can add a little bit more structure in what's called an inductive groupoid. So as the name suggests, this is obviously a groupoid. Specifically, it's an ordered groupoid. And by that I mean that I have a partial order on our collection of morphisms. And that partial order needs to satisfy four axioms, which I'm not going to go through. In terms of an object set, well, it is a meet semilattice. So that means if I take any 2 points, they always have a greatest common lower bound. Now, just setting up some notation, I want to be able to talk about the category of inductive groupoids, and I'm going to denote it like this. And just so we sort of keep track, what was the underlying category structure? It was an ordered groupoid. And what was our object set? Well, it was a meet semilattice. So if I now go back in time, symmetry arises naturally in nature, and this led to the notion of an abstract group by Cayley in 1854. Symmetries also arise in differential equations. This led to the notion of a pseudo-group by Lie in the 1880s. But there was no abstract structure for these until eventually two solutions were found in the 1950s. One using inverse semigroups by Wagner and independently Preston, and a second one using groupoids by Ehresmann. Schein in 1965 then takes the work of Wagner and Ehresmann by providing a structure theorem for inverse semigroups that makes use of groupoids. Namburipart in 1979 takes this one step further and generalizes the result from inverse semigroups to regular semigroups. That brings us to the classical ESN theorem that we know today as formulated by Lawson in 1998. And basically what this is saying, if I take my category of inverse semigroups, it is isomorphic in the category sense to the category of inductive groupoids, which I just went through with you. Since then, there's been a lot of efforts to try and generalize this to other semigroup families. And first up was Lawson in 1991, where he proved the analogous result for Ehresmann semigroups. So that is, the category of Ehresmann semigroups is isomorphic to the category of Ehresmann categories, which have a category structure of a bi-ordered category. So now we have two partial orders on our collection of morphisms. And our object set, though, is still a meet semilattice. And in the same paper, Lawson also proved the analogous result for the restriction semigroups. Before I continue, we need to take a quick detour into some projection algebras and understand what these are. So let's take our entire semigroup S, and let's look at the set of idempotents inside of it. So x is equal to x squared, that's an idempotent. And sitting inside of that, we have our set of projections. So not only are they idempotents, but they satisfy the additional condition that the domain and range map is the identity on these set of projections. An alternative but equivalent definition comes from the DRC axioms, from which we can see quite easily that the image of the domain and range map are actually the same. And I can use this common image just to be defined to be my set of projections. Unfortunately, the set of projections are not always going to be a sub-semigroup, but I can turn it into a projection algebra, where I have two families of unary operators, so one for every projection. So the feeders are defined in terms of the range map, and sort of dually, the deltas are defined in terms of the domain map. Naturally, these need to satisfy some axioms which I'm giving here. And for those of you that are familiar with it, do be careful. This is different to Peter Jones's original formulation of a projection algebra, where he made use of two binary operations. But the two are equivalent if we make use of these two identities. So that brings us to last year, where East and Muhammed proved the analogous result for the regular star semigroups. So that is, the category of regular star semigroups is isomorphic to the category of chain projection groupoids. Here we have a category structure of an ordered groupoid that we saw earlier, and our object set now is this projection algebra that I just went through with you. Also last year, D and Wang proved the analogous result for the DRC restriction semigroups. And at this point, I should mention there are other generalizations by many other authors that don't quite neatly fit into this picture, but a lot of work has been done in this particular space. That brings us to the DRC ESN theorem, and that's the key result I want to talk to you about today. So this is the statement of the theorem, and basically what it's saying is if I take the category of DRC semigroups, this is isomorphic to the category of chain projection categories. In terms of a proof of this result, well, first I need to find the right axiomatization of the category, which for us is a bi-ordered category, so the same that we saw in the Ehresmann case. And we need to find the right structure of objects, which for us is the projection algebra we just saw a moment ago. So let's look at this isomorphism in a little bit more detail. So I start off with a DRC semigroup S, and ideally I need to associate to it a chain projection category. And I'm writing it at the bottom here because we have a lot of constructing to do to get there. We already saw how I can go from my semigroup to a projection algebra. So my set of objects is now going to be this projection algebra. And my morphisms, well, that is actually going to be the entire semigroup. So let's put this into a picture to get a little bit of a better understanding. So if I take an arbitrary x in my semigroup, that's a morphism. Morphisms are denoted by arrows. I can take a different element, let's say y, that's going to be a different morphism, a different arrow. Now recall that the image of the domain and range map is precisely our set of projections, our object set. So if I now think of where does x map from? Well, if I take the domain of x, that is now going to be an object, and it logically makes sense that x is going to map from the domain of x. Likewise, where is it going to map to? Well, if we take the range of x, again, that's an object, and it makes sense that it maps to the range of x. So here we can start to see that the terminology, and in a moment, some of the axioms from the DRC semigroup kind of make canonical sense. Likewise, if we look at y, where is that going to map from? Well, that's going to map from the domain of y to the range of y, and in this example, I'm just going to suppose these two are equal. We do need some identity morphisms. So for this, recall that on the set of projections, our range and domain map are the identity map. So this d of x is some projection, let's suppose it's p, but this is also an element in our semigroup. So let's think of it as a morphism and ask, where does it map from? Well, it's going to map from the domain of p, but that's just p. And where's it going to map to? Well, the range of p, but that is also just p. So we can see that p, thinking of it as a morphism, is just going to map from p to itself again, exactly the identity that we wanted. And likewise, the same is true for the other objects in my little example here. Composition, well, basically I'm going to use the semigroup product for composition. So composition would mean I need to have a morphism from the domain of x to the range of y, and I'm going to hope that the morphism x times y in the semigroup is going to satisfy this need. For this to work though, we need the domain of xy to equal the domain of x. Is that the case? Well, with perfect foresight, recall these two DRC axioms, and let's have a look at the domain of x and y. If I apply the first axiom, I get this, where we have a domain of y sitting inside. Domain of y by assumption is the range of x. Let's make that substitution. Here I can now make use of the second identity, and I get back the domain of x. Yes, domain of x and domain of xy are the same as we had hoped. And by dual argument, we're going to get that the range of y is equal to the range of xy. Because I'm basically using the semigroup product, I get associativity of composition for free because obviously the product in a semigroup is already associative. So this construction gives me what's called a projection category. So I can take a DRC semigroup S and map it to its associated projection category. Suppose I take another DRC semigroup, say T, I can also map that to its associated projection category. Problem is, S and T could be two different DRC semigroups, but they map to exactly the same projection category. That's not great if I'm trying to prove an isomorphism and I need injectivity. So to get around this, I need to introduce an evaluation map epsilon, which I'm not going to explain or define in any detail because it does get a bit involved, other than just to very hand-wavily say that in precisely this situation, the evaluation of S is different to the evaluation of T, and hence we recover injectivity. And this construction then is my chain projection category, which is this triple: our projection algebra, our projection category, and this evaluation map. Next step is to then take one of these triples and see how can we go back to a DRC semigroup, and then show that both directions do actually give us an isomorphism. I'm not going to go through these last two steps today. So if we recall the complexity analysis that we did at the start, let's look at that in practice for the four categories that I explicitly mentioned. So in the inverse case, we had the inductive groupoid, and in the DRC case, we had the chain projection categories. If I move up by the regular star case, we move through the chain projection groupoids. So if we look at the category structure, we go from an ordered groupoid to an ordered groupoid. So we're not changing the structure at all here. But if we look at the object set, we go from a meet semi-ladders and upgrade it to a projection algebra. We're adding more structure here. Likewise, we didn't need an evaluation map down here, but we do need it here. And then, of course, these two get translated and used in the DRC setting as well. Now, if I go up via the Erisman category side, if we look at the category structure, I go from an ordered groupoid to a bi-ordered category. So we have an increase in structure here. But our object set stays the same with a meet semi-ladders, and we don't need the evaluation map. And then this bi-ordered category also is required in the DRC setting. There are some applications for this work, but for us to understand those, we first need to understand what I mean by projection generated. And basically, I just mean that the set of generators is the set of projections. A corollary of this result is that we can generate free projection-generated DRC semigroups. If that sounds like a little bit of a mouthful, basically just think of it as a free semigroup, where our set of generators is a set of projections, and what we end up with happens to be a DRC semigroup. Another corollary is if I were just to take an arbitrary projection algebra, I know that it's a projection algebra for some DRC semigroup S. This result was already known by Peter Jones in 2021, but he made use of different proof techniques. To conclude, I hope I've given you a high-level summary of what this project was all about, but if you do want to know a little bit more about the nitty-gritty details, please do have a look at our Journal of Algebra paper. There are some possible future directions for this work, the most obvious one being this star regular case, and some of our collaborators are actually working on this at the moment. Then there was these weaker semigroups that I briefly mentioned as we were on our way to defining the DRC semigroups. They remain yet to be done, and the holy grail for this research program would be the ESN style theorem for just an arbitrary semigroup. If I go back to the start where I said this was going to be a tale of two cities, semigroup city and category city, well, in fact, it actually is just a tale of one city thanks to the strength of category theory.